Good data is the foundation of good science. For over 50 years, people around the world have been collecting water samples from which isotopic analyses can be used to get isotope ratios. Now, although at any location a time series or other sorts of measurements of isotope ratios are very helpful to understand local hydrology, for instance, the collection of samples around the world allows patterns of isotope ratios in precipitation to give us a regional context for those measurements. Here we see a map that compiles isotope ratio data from many sites over those 50 years, and we see lots of patterns that emerge. For instance, we see that in the tropics over the oceans, the lack of shading is indicating high values, whereas towards the polar regions and towards continental interiors, the isotope ratios are lower. And indeed, at high altitudes, we also see lower values. These three things all come together over Antarctica. It's both towards the poles, high altitude, and the interior of the continent, where the lowest values are found. So what is it that controls this fundamental pattern, this distribution? What is underlying this pattern? So one way we can start is to think about precipitation itself. Let's imagine an air parcel with water vapor in it, and some fraction of that water vapor will be both heavy and light isotopologues in their relative abundance, this giving us the isotope ratio. Now, if we have condensation occurring, that mass will be split into parts, one part being vapor that remains, the other part being the precipitation or the condensate which forms. We can think about rain and raindrops. Now, in terms of the isotopic fractionation, there will be an isotopic fractionation, leaving the isotope ratio of the vapor different from the isotope ratio of the condensate. In fact, the isotope ratio of the condensate will be slightly heavier by the fractionation factor, the equilibrium fractionation. So comparing these values to our original isotope ratio, R0, the vapor will be lower and the condensate will be higher. So moving forwards, if we continue along and we imagine that the air mass continues and there's a further condensation event, again we'll see a separation with the condensate and the vapor continuing on even further, but now the isotope ratio of the condensate, again with fractionation, will be less than the isotope ratio of our very original isotope ratio in the vapor. So too, the isotope ratio in the vapor will now be even lower again, so lighter isotope ratios. We can do this quantitatively as well. What we're after is figuring out how the isotope ratio of the vapor changes relative to the amount of water that's removed as condensation or as precipitation. So we can write down for our ratio, the ratio of heavy to light isotopes, that the change in the isotope ratio will depend on both the isotope ratio itself, but also the fractionation factor. We know that as precipitation is removed, the heavier isotopes are removed slightly preferentially. With a little bit of algebra, we can write down an equation that we can integrate, leading to an equation that relates our final isotope ratio to simply the amount of water vapor that remains, F. Here we have F being the number of molecules or the amount of water vapor that remains compared to the number of molecules we had to begin with. This is the Rayleigh distillation model, and it describes the isotopic rainout effect as water vapor is continually removed and the heavier isotopes are removed preferentially. Notice it depends principally on the fractionation factor alpha, but also just the rainout amount, F. So let's have a look at what this relationship looks like. Let's make an analysis of the isotope ratio as a function of the rainout fraction F. Initially, we have our parcel of air with some initial isotope ratio, and we have 100% of the water, so F equals 1. If we have condensation, we have the decrease in the isotope ratio as F approaches 0. Ultimately, as F goes to 0, R becomes essentially 0 as well, which gives us a delta value of minus 1000. Now this is for the vapor. We can also think of how the precipitation might change with this, that we know the precipitation is in isotopic equilibrium with the vapor, so at any point along the way, we have just the equilibrium fractionation to give us the isotope ratio of condensation. Now, our Rayleigh distillation model works quite well in the atmosphere, and it works equally well under evaporation conditions. So let's consider the alternate. Let's imagine an isotope ratio of an original soil moisture amount. And as we have now evaporation, which has a preferential evaporation of the lighter isotopes, we can again use the Rayleigh distillation model, but now we have, during evaporation, 1 on alpha, the inverse of the fractionation factor. So as time goes by, the liquid in the soil water, becomes increasingly enriched as time goes by, and similarly, the vapor associated with that evaporation, the evaporated vapor, would be in isotopic equilibrium. This is just the same type of curve, but it's inverted relative to the precipitation. So going back to our precipitation map, we saw these patterns that indicated that where we had inland incontinence towards the polar regions and at higher altitudes, lower isotope values. We can relate this all to the idea that F is a smaller value in these areas, that F, principally controlled by the temperature and the saturation vapor pressure, is telling us that places which are colder, drier, are going to have both lower F and then ultimately lower isotope ratios themselves. This explains many of the principal patterns that we see. And in fact, this was the basis for thinking about how to obtain estimates of temperature from past climate conditions from ice cores. If we were to look at the isotope ratio of ice compiled as piles of snow in the polar regions, the isotope ratio is telling us something about how much condensation there has been, what is the value of F, which we know is related to temperature through the Clausius-Clapeyron relationship. So ultimately we can use measurements of the isotope ratio of snow to infer past temperatures. Now of course, this model is useful and gives us a great deal of intuition, but it's not the complete story. It's only strictly valid when the air mass itself is isolated and there's no air mass mixing. So if we have more complicated systems, like the real Earth, we have to consider more complex models that account for mixing. Thanks.